Today, we embark on an exploration of one of the captivating narratives hidden within the vastness of space. This tale doesn't unfold among the sparkling brilliance of stars or the swirling beauty of spiral galaxies. Instead, it centers around the enigmatic and dense entities that populate the cosmos' neutron stars. Our journey commences with a spectacular conclusion, the explosive demise of a massive star through a supernova event. In this celestial spectacle, the death throes of the star give rise to something extraordinary, the birth of a neutron star. These stellar remnants are so densely packed that a mere teaspoon of their material weighs as much as a mountain on Earth. Yet, the narrative takes a riveting turn when these neutron stars find themselves in the company of their cosmic counterpart. What secrets do they unveil when gravity and light engage in a cataclysmic dance? Today, we are poised to witness extreme physics in action, delving into the rippling fabric of space-time and eavesdropping on the whispers of the universe through gravitational waves. In the vast cosmic theater, the life of a star unfolds as a saga of transformation and energy. We begin with a colossal star, surpassing our sun in mass. At its core, a fierce battle rages between gravity and nuclear forces, where hydrogen atoms fuse to form helium, releasing prodigious amounts of energy. However, this stellar furnace is not eternal. As the star depletes its hydrogen fuel, it undergoes a series of transformative phases. The core contracts under the relentless pull of gravity, igniting helium in a brief but intense phase known as helium burning. The star then expands into a red supergiant before culminating in a dramatic supernova explosion. In less than a second, the core collapses catastrophically, giving rise to a neutron star. These neutron stars, born from the ashes of a supernova, are both bizarre and exotic, incredibly small, yet phenomenally dense. As we venture deeper into their mysteries, we discover the neutron star's magnetic fields, trillions of times stronger than Earth's. These powerful magnetic fields are the orchestrators of dynamic cosmic phenomena, such as the emission of powerful radiation beams. Within the neutron star, a peculiar world emerges, a crust of nuclei immersed in a sea of electrons, evolving into a state known as nuclear pasta. The neutron star's journey unfolds from the agony of a massive star to the birth of one of the most mysterious entities in the cosmos. Their extreme density, magnetic fields, and unique internal structure transform neutron stars into cosmic laboratories, allowing us to study physics under conditions impossible to replicate on Earth. But neutron stars are not solitary entities in the cosmic expanse. Some exist in binary systems, bound by the gravitational dance between them. This stellar duet, characterized by immense energy and complexity, leads to profound effects on each other and their celestial surroundings. Gravitational waves, emitted as these neutron stars orbit each other, create ripples in spacetime, offering a unique lens through which we can observe the universe. In these binary systems, neutron stars exert their gravitational influence, inducing phenomena such as mass transfer, explosive events, and even the formation of black holes. Their intense magnetic fields and radiation can alter the environments of nearby planets, providing insights into the survival of celestial bodies in extreme conditions. Moving through space, neutron stars interact with the interstellar medium, creating radiation signatures and complex structures such as shockwaves. The study of these interactions offers valuable insights into the diversity of planetary systems and the impact of neutron stars on their cosmic neighborhood. The cosmic stage further unfolds with the introduction of pulsars, the beacons of the galaxy. These rapidly rotating neutron stars emit focused beams of electromagnetic radiation, resembling the sweeping light of a lighthouse. Pulsars, with their remarkable regularity, serve as cosmic timekeepers, allowing astronomers to explore phenomena like gravitational waves and the interstellar medium. Neutron stars, however, don't always traverse the cosmos alone. In binary systems, they engage in a gravitational pass-to-do, influencing each other and creating intricate astronomical phenomena. The study of these systems offers a glimpse into the dynamic nature of neutron stars as active participants in the cosmic landscape. Among the most awe-inspiring events in the universe is the Kilonova, a colossal explosion resulting from the collision of two neutron stars. This cataclysmic occurrence, beyond being a cosmic fireworks display, acts as a crucible for forging some of the universe's most precious elements. The collision produces gravitational waves that vibrate through spacetime, offering a symphony of information about the universe's composition. In the crucible of a kilonova, neutron stars collide with such force that they distort spacetime and release energy surpassing even the brightest galaxies. What makes this event truly remarkable is its role in the creation of heavy elements through the rapid neutron capture process. Elements like gold, platinum, and uranium are birthed in the fiery aftermath, contributing to the cosmic tapestry. As we delve into the profound impact of neutron stars on our understanding of the universe, we recognize them not merely as astronomical curiosities, but as key players in extreme physics and multi-messenger astronomy. Neutron stars offer a unique opportunity to study the most extreme stages of stellar evolution, with their collisions emitting gravitational waves that provide unprecedented insights. The simultaneous detection of gravitational and electromagnetic waves from neutron star collisions marks a new era in astronomy. This multi-channel approach allows scientists to not only hear the gravitational waves, but also witness the colors of light, offering a holistic understanding of cosmic events. The fusion of these observations opens new avenues for exploring the universe and testing fundamental theories, including Einstein's theory of general relativity. Looking to the future, the study of neutron stars stands on the cusp of groundbreaking discoveries. Advanced missions and projects, equipped with state-of-the-art technology, aim to observe neutron stars across various wavelengths. The increased sensitivity of gravitational wave detectors promises more precise studies, unraveling the intricacies of neutron stars' properties and behaviors. The ongoing and upcoming missions hold the potential to answer fundamental questions about the state of matter under extreme conditions. Beyond advancing our understanding of neutron stars, this research has far-reaching implications for astrophysics and cosmology, addressing fundamental questions about the expansion of the universe and its underlying physics. In conclusion, the study of neutron stars offers a captivating journey into the depths of space and the frontiers of scientific discovery. These celestial entities, born from the cosmic drama of stellar evolution, are not only captivating in their own right, but also serve as cosmic messengers, revealing the secrets of the universe in ways we are only beginning to comprehend. As we look to the future, the exploration of neutron stars promises to inspire generations of scientists and astronomers to venture into the uncharted depths of space, unraveling the mysteries that lie beyond the boundaries of our cosmic horizon.